Good afternoon. My name is Thomas Cort, and today I'm going to tell you about developing device drivers on Linux and sort of try to take away some of the mystery out of device driver development and hopefully inspire some more people to work on device drivers. Just a little bit about myself before we begin. I was a former Google Summer of Code student for a few years, working on Unix domain sockets and porting software, and most recently working on the I2C drivers for the BeagleBone Black. I do some Minix work for fun as well. I've imported and tested 90 plus programs from the NetBSD userland and done several minor patches. So what sort of qualifies me for this talk? I developed the I2C bus driver for the BeagleBone and the BeagleBoard XM. I've worked on I2C sensors for the weather cape. It's an expansion board for the BeagleBone. Worked on the power management chips on those boards. I ported the GPIO driver to the BeagleBone. Worked on rebooting and powering off those boards. So the goal of my talk today is sort of to inspire more people to work on device drivers. That's one area where Minix is really thin. There's been a lot of work on the really cool aspects of the microkernel, but it's not very practical if you can only run it in a virtual machine. So how are we going to get there? Well, I'm going to show you how to go from an idea and turn that into code and get it contributed to Minix and all the steps involved, and I'll go over some tips for submitting the best possible code that you can and for debugging and preventing bugs. Before that, I just want to whet your appetite a little bit and tell you why developing device drivers for Minix is a pleasure. I've developed some drivers for other operating systems in the past, and when you have a bug or an infinite loop that causes it to crash or freeze, you have to sort of hard power down the system by pressing the reset button and have your fingers and toes crossed that the file system isn't totally corrupted. With Minix, it's just a regular process on your computer, and you can stop it and start it and kill it. And Minix drivers in general are single-threaded. You're only dealing with one request at a time, so that removes a whole layer of complexity with different threads and locking and mutexes. And the interface between drivers is really well defined. You're dealing with a set of messages, and they're all documented on the wiki. You don't have arbitrary points in the system just calling into it. It's all through the messaging system. So when you're going to choose a device to write a driver for, you should look to see if it's already supported or partially supported, or if there's a similar device. Sometimes with network cards, it's as easy as just adding a PCI ID or just a few lines of code. You can check on the Minix Google group if anyone's already working on the driver for that device. You want to make sure that there's documentation available so that you actually have enough that you can build a working driver. Hardware availability is another important point. It's great that you can write a driver for a 20-year-old printer that's not being made anymore, but it's not as useful as something that someone else could buy or someone else is going to actually use with Minix. It's also helpful if there are other open source operating systems that you can look at for help. Sometimes it's easy to port a driver. Other times you can at least get some inspiration. If you're having some weird timing issue, you can see, what order are they writing to the registers in, and what sort of values are they using, what frequency did they set the clock to, and that can sort of make things a little clearer. And also make sure that the device can be used with Minix. You can't really write a USB device driver if you don't have a USB bus in Minix. So when you first begin, study existing Minix drivers as much as you can, and look to the Minix wiki. There's a Hello World driver tutorial, and there's most of what you can learn is in the Minix source code itself. Look at drivers for similar devices. There are system reference manuals. Those are sort of more at the board level. So like the BeagleBone, there's a whole huge PDF that covers all of the pinouts, all the different chips that are on the board. And then drilling down a little deeper, there's technical reference manuals. The AM335X, which is the system on a chip on the BeagleBone, has like a huge manual that's tens of megabytes. There's data sheets for individual chips, and some device manufacturers also provide a software development kit with sample code that you can reuse, and you can also look to other operating systems as long as you respect the license. So before you really dive into developing code, it's important to eliminate some sources of error before you begin. So start with good hardware that you've tested with another operating system. Also test the computer with Minix to make sure that it's stable. For example, if it's an x86 system, try rebuilding the whole system from source code. If that works, it's a pretty good measure that your system is functioning properly. If you're working on any subsystem or that has some sort of external interface, try to follow what NetBSD does. With I2C drivers, that's what we did for the userland interface. We just copied what NetBSD had, which was the same as OpenBSD. So that made it really easy to import some userland utilities from NetBSD. There's an I2C scan program which will enumerate the devices on the bus, and that's just a userland program. And I was able to import that with minimal changes. And if it's an existing class of device, just follow what Minix does. So like for network drivers, don't reinvent the wheel, just sort of do the same style that other network drivers already use. So as a case study to sort of go through what exactly comprises the driver, we're going to look at the BMP085 temperature sensor. It also measures barometric pressure. It's an I2C device on the weather cape expansion board for the BeagleBone. So the first thing you need to do is find a place to actually put the source code for your file driver. And under user source Minix, there's a drivers directory. Under there, there's different categories of drivers. You pick the most appropriate one. This one's a sensor, so it goes under sensors. It's a pretty simple driver, so there's only one C file and make file. Sort of in the parent directory and the sensors directory, we need to tell the build system to traverse into our driver's source directory. So we just add it to the subdir variable. In this case, we're only building this driver on ARM because ARM is the only one with an I2C bus at the moment. And there's no point in having this driver compiled if there's no way to use it on x86 systems. And then there's the makefile for the driver itself. You sort of list the name of the driver, the source code files. You find all the dependencies and list those, as well as the libraries for the linker. This file, this driver uses the timers library because it has to do a small delay between when it tells the chip to read the temperature and when the reading is actually complete. It uses the sys library, which has some of the interfaces for doing safe copy to grants. It's a character device driver and leverages some of the functions provided in that library. And it also takes advantage of some of the functions in the I2C library. Your goal should be to sort of reuse as much as possible and leverage all of the existing code when you can. We also include the BSD source directory includes so that we can get a few other header files. There are some for doing debug logging and things like that. And I like to include a README file, but it isn't mandatory. But if you do provide one, sort of try to answer some of these questions, like what does the driver do? What's in each source file? How do you start, stop, and test the driver? Are there command line options that you need to supply? Are there any limitations? A lot of these devices have a lot of different configurable options, but only sort of one way is implemented. So for example, with a lot of the sensors, you can make the trade-off between how much time the sampling takes and how much power you use and the precision. But in the case of the BMP-085, I just went with the sort of default settings. And the limitation section also gives the next person to come along an idea of other things they can work on in the driver. And then you also want to give some links to data sheets or other sources of information for other people that are going to come along and work on the driver as well. In etcsystem.conf, that's basically the permissions for all the different services within Linux. And this driver is really simple, and it just needs to communicate with some other services, the reincarnation service, the I2C bus driver, DS in the system. Other drivers have more complicated settings. You can say what IRQs they can go on, what UID they run as, but in general, try to keep the permissions as minimal as possible, only what it needs to do its job. And with Minix, it uses the concept of distribution sets from NetBSD, and you enumerate all of the files that are installed in the base system, and at the end of the build, it will compare the files in the destination directory with what's in these lists, and if the two don't match, it'll give you an error. It's good to spot when you have extra files or you're missing files. That's a smell that something's gone wrong with your build system or your make files. You commented something out or added something and didn't put it in the list. Sort of to dive into the source code of the sample driver, I've sort of commented some stuff out and shortened it to be able to fit it on a slide, but it'll give you a general idea of what's inside a driver. It's just like a regular program. There's a main function, and with I2C drivers, because there are multiple buses and devices can be on different buses and devices can have configurable addresses, you have to pass the number of the bus and the address that the device is on to the driver. Sometimes it's not always possible to enumerate all the devices on the bus, especially with the controllers on the BeagleBone and BeagleBoard. And so the I2C driver has a library function to grab those options from the command line. And then there's a startup function which does the initialization, and then there's the main program loop, which is taken care of by the character driver library. And I'll sort of dive deeper into each of those in the next slides. For the system event framework, there's initialization functions, and you create a callback, and you pass the function pointer to set those callbacks. There's one for fresh, when the driver first starts up, one for live update, and one for restart when you're restarting your driver. For the sort of old style live update, you supply a function that will save the state of the driver, and in your initialization function, it will restore that state. And then you call Ceph startup, and that will call the initial callback to do a fresh start. So in that function for this driver, if it's a live update, it'll restore the previous state. Otherwise, it'll reserve the address on the bus with the bus driver. it'll do some initialization, and then it'll announce to the world that it's up and running and ready for service. For the sort of old style live update, you basically publish your state information. In this case, the state is really simple. It's just the number of the bus and the address of the device. And then for restoring the state, it's just the inverse. You retrieve those two values, and then just save them to your process. And then initialization code for the device. The first function you want to write is a version check function. Most devices have like a chip ID or a version number that you can read off the device. You should do that to make sure that you can communicate with the device and that it responds. And that sort of gives you at least a base sense of the device is powered on and sort of works. In this particular driver, it also has to read some calibration coefficients off the device that are specific to that particular chip that are used when calculating the correct temperature. And when you're using the chart driver library, you can supply a set of callbacks for each of the operations, like read and write and IOCTL. In this case, the only operations are read and other. And so I'm just applying those two. And the read function, just basically taking the temperature and pressure measurements and filling a buffer and then copying it to a grant that is passed to this read function and then returning how many bytes were read. Within the actual measurement that's communicating with the device, it does it through some wrapper functions that were written that basically send a write command to the I2C bus controller with the values to trigger a temperature reading. There's a micro delay that waits for the sampling to complete and then it reads back the result. So my number one tips for debugging are to make a lot of small changes and compile and test after each change. And try to do as much logging as you can with the log.h file. A lot of people use like hardware debuggers, but I find it's just too complicated and it's much easier to just print out what all the variables are. But sometimes you do have to use a hardware debugger, and if you're working on the BeagleBone and you need a hardware debugger, there's one on the BeagleBone White, which is useful. And I'd suggest avoiding hardware simulators when possible. I've used QEMU before, and the code worked in QEMU, but not on the real hardware. Sometimes you'll run into timing issues when you actually try it on real hardware. So once you have your driver written, there's sort of a checklist I came up with for figuring out if it's ready to go. You have to make sure your code compiles without any warnings. It's a good indicator that at least the compiler thinks it's okay. Make sure you didn't break the build for the other platform. So if you're working on a driver for ARM, make sure x86 still works. Does it work as advertised? Is the driver stable? Does it impact performance? Try to break up your changes into a series of small commits that each do one thing with a well-written commit message. Try to be as consistent with the style of other device drivers as possible. Code that's been accepted before is likely to be accepted again. So try to be consistent. For new code, try to go with the NetBSD coding style. If you're updating existing code that's in the Minix format, just keep it like that. Double check that you've complied with all applicable licenses and have given proper credit to your collaborators. can discuss your changes on the Minix Dev Google group. There's also an IRC channel. Submitting your code can be done on GitHub, and be receptive to feedback and requests for changes when you do submit your code. Are there any questions?
That's time to figure. Questions? Can you tell me, what are the differences between developing for drivers for ARM platform and for x86? What would you say?
The main difference is that ARM isn't self-hosting, so you have to do like a lot of cross-compiling. On x86, you can sort of just do it live on your machine. With ARM, you have to like cross-compile it and copy the files over.
But if you make some sort of driver which is say a virtual driver.
Okay.
It's supposed to work on both platforms like that, or is there something which is specific, which should one look for certain platform?
Like in general, if the device would work with either x86 or ARM, you should try to make it generic so that it works on both.
And there's a reason why I'm asking this. I've developed, as I said before, link aggregation driver. I tried to compile it on BeagleBone Black. Worked just in one interface. There was only one, and it didn't work. And it should. So I'm not sure why. Because it doesn't have to do anything with hardware. It actually communicates with Ethernet driver for BeagleBone Black. So
yeah, it was something like a link aggregator. It should work on both.
So it should work on both. Okay, so probably something I misconfigured. Thank you. Other questions? Yes.
So I might have missed, but one thing that I didn't hear mentioned in the talk was testing. If you have the right test code,
In general, it's hard to do a lot of testing with test code. It's hard to test unplugging something and plugging it back in, or testing that the temperature sensor reads the temperature in the room. When I was developing some drivers, I sort of wrote up a test plan, like a list of steps, like, oh, if you run these commands, then you should get this output. But I didn't develop any sort of automated tests that are part of the test suite.
there's no mocking going on.
How practical is it to experiment with the BMP-085 without the cape? Can you get them standalone? Because that way you could use them on a middle board, I2C bus, or any other computer.
Yeah, I think that one is available standalone. I don't think there's a Minix driver for I2C on x86, so someone would have to write the driver for that. But if you wanted to use it standalone with a BeagleBone or BeagleBoard XM, it should work.
Other questions?
There's even one quite often to make an I2C driver for x86 maybe not true, but what we saw so far is that the existing I2C driver is very close written to ARM. So means even the whole native file is represented with to ARM.
So my main focus at that time was for ARM, but it is like the ARM specific code is split out into another file. So the main like I2C bus like C file is there, and you just have to substitute in your own process function, and that takes a structure that is similar to the NetBSD I2C interface, where it just has the command that you run, that it's supposed to be running, and the results. Okay.
I can perhaps add to that that on average the ARM port cost to discover those differences between operating systems. So while doing that port, we would, at the point when we know split the drivers into the generic part and the operating system, hardware specific part. And you see that in most of the code, this code actually the opposite probably shouldn't happen. It's working on ARM, and the moment you port it to the second part of the platform is probably the best moment to split, because you know exactly what interface you'll have to apply.
But there's a lot of generic stuff that's separated out. Like there's a list of reserved device addresses and buses that's in the generic part, not in the ARM part, stuff like that.
Okay, it's things I saw already before, but my point is more like it's also the whole packaging process and things like that. It's only for ARM. And so at the end, we could already bundle it for the x86-2, that even if there's no possible controller for the I2C bus, supported at all, because then at least it's already there. Okay, it might not work, but it's already there on the wall, and it would be easier for others to start adding only the remaining functionality in the hardware device section.
Yeah, I guess it's sort of a trade-off, because like you're compiling all that code for x86 that doesn't work or doesn't get run. Then you're building for x86 and you don't have support for the controller.
It will compile, it will also run, but it's done correctly. The device out of the register will be there. The hardware device, if it's not there, it will just tell you, okay, no, nothing here, or something like that. If you use it via that I2C, maybe that's an idea if you don't want to trade-off.
Yeah, like it's easy to just edit the make file and adjust the distribution sets, but yeah. Anything else?
I wasn't 100% clear about the privileges. Do you, when you're starting up, do you have to be running as root in order to obtain access to the the addresses that you need? And are you then able to drop privileges? And when you're doing your reinitialization callbacks, do they still work with drop privileges, or do you need to be root the whole time, or how does that work?
So the temperature sensor driver doesn't access any hardware itself. It goes to the I2C bus, and for that, in the service.conf file, there's a list of addresses that it can access for the different controllers, and the system will grant it access to those. And in the startup code for the I2C driver, it'll say, please give me access to these addresses, and they have to match what's in the service.conf file. And that's how it's done.
Makes sense.
It doesn't need extra privileges to drop, it just has them to begin with.
Any other questions? And then maybe a last question. We all know that the ARM port hasn't been completed, so there's a lot of devices for which we don't have support yet. Could you recommend some device which is particularly interesting to write a driver for?
Perhaps the SPI bus. It probably, you could copy a lot of the work from the I2C bus and use that as a starting point.
All right, let's thank the speaker one more time.